All right, welcome to Stylight. So tonight we are hosting the TensorFlow Meetup, and we have Natalia here, who's going to be the master of ceremony for the evening. So Natalia.
Thank you, Johan. So welcome everybody. Welcome to our first meetup on TensorFlow in Munich. I'm glad you're here, and I'm excited that we're going to have an exciting program and agenda for today. Thank you again, Stylight, for hosting us. That's a really great place, so thank you. So my name is Natalia. I'm with L Taurus, and we're organizing this TensorFlow meetup. I'll do my best so that at least some of you come back for the next meetups, and probably some of you would like to become guest speakers next time. So if you want to share anything about what you've learned on TensorFlow, please reach out, and we'll be glad to have you. So that said, I'm again would like to highlight that we have a great lineup of speakers today, and we're going to make some interactive agenda, and that is why we're going to have fireside chats, the format of fireside chats, questions and answer sessions. So please be proactive and ask your questions, and probably make your comments if you have any, so that we could make a real discussion. And then we will have two talks on TensorFlow, the overview and a deeper dive on this. And we're also going to discuss a little bit of OpenAI, as this is not the main focus of our group. However, we will have the first meetup joined a little bit with the OpenAI, and we'll be glad to hear what you think of this, of the nonprofit organization and of open source artificial intelligence in general. But this will be the second part of our meetup. So for the first part, I would like you to welcome our first guests. There will be Alex Osterloher coming from Google, and we will have Artem coming from Data Reply, and we'll have a fireside chat with them. Hey guys, where are you? Hello.
Yep.
Yeah.
So, okay, I'll start. My name is Alex. I've been with Google for about 5 years. I took a bike ride over here. It took 6 minutes because we just moved, so we ran out of space. We had, can you hear me, see me?
Yes.
Everything good?
Yeah.
We had 3 offices. Now we have a big new office right on the S-Bahn between Donnersberger Brücke and Hackerbrücke, where we could potentially also host a meetup very soon.
Yeah,
so
nice.
they're building right now some of the bigger meeting rooms. They're not quite ready yet. So I'm from Google. That's I guess pretty cool from a machine learning kind of aspect. The downside of me being here is that I don't have a clue about machine learning. But my first 4 years I worked for the search team. I worked for Google for Work, first of all. They sell search solutions, geo solutions for enterprises. I don't know who here has ever seen a Google search appliance? Okay, a couple, all right. So that's kind of what I did my first 4 years, and since a year I moved over as a sales engineer into the cloud platform team, covering rather big region here in Europe, and in this regard I cover all the big data topics, so anything that has to do with managed services. So Google is starting to open up many of its internal tools that we use internally at Google, like you've heard of Dremel and these kind of tools that we're starting to externalize. And if I want to keep my job at Google for a while, which I intend to do, I will not talk about any roadmap or any future in the machine learning space, but if you're interested, contact me. We'll set up a meeting, sign an NDA, and we can talk a little bit of what's coming up, because we're pretty open. We're pretty late to the game in the cloud, right? Amazon opened the doors with being able to spin up virtual machines rather easily. Google's more going the route of no touch of infrastructure, having managed services to build, big data processing pipelines. I understand machine learning is potentially a important part of this. We started with TensorFlow, and there's likely other things coming down the road. You might have heard of the Vision API. Anybody? Or checked it out? It's public beta now, so we will probably have more pre-trained data sets that you can use for not just images but other types of media as well in the future. So yeah, that's me, and I brought a little support in form from Archam, from partner Data Reply. He's been looking at TensorFlow a lot more deeply. Maybe quick introduction.
Yeah, Alex, please introduce yourself and let us know what you're working on.
Hi, so I'm Archam, as Alex said. Then I did my master's here in Munich, and then back then I used to work in the biomedical robotics and machine learning lab here. So I did a bunch of deep learning with a bunch of people who were much smarter than me, but back then, this was like a few years ago, there was only Theano, like all the deep learning toolkits. There were like 2 or 3 which were kind of okay. It's like some of them became like really nice, so I used them a lot. Now there's like 500 of them, and also like TensorFlow as well. So kind of when it came out, started looking at it a lot. And it was actually quite interesting the way it worked, more distributed processing than neural network thing, to be honest. But this will probably come up in the other talks, right, as well. But I'm from Data Reply, and we're like a company here in Munich which do like big data and data science. We specialize in that. And then we've used like neural networks in a bunch of projects, specifically like deep learning, mostly for visual analysis and stuff like this. So like, classical convolutional networks. So I hope we can answer all the questions that we can. But I think there's like good talks coming after us as well, right? So
yeah, absolutely.
Yeah.
So if you don't like this part, it can only...
Yeah, we're like fluffing everybody. It's gonna be great.
Okay, but you've mentioned that you've had some real experience with TensorFlow. So can you share with us what kind of problems and tasks TensorFlow is good for in comparison with other toolkits?
Well, like the main thing with with TensorFlow that we noticed, especially when like it's very easy, like basically this is a thing that's not talked a lot at all in research, is actually using the models for something. Like not everybody trains a model, they plot a nice graph, okay, this model outperforms everything, you win a Kaggle challenge, that's nice, but nobody actually uses the model in any kind of real way, because like for example Theano or like PyCudo or something, if you just make the model in those, the startup times are horrible, the dependencies like to manage all of this stuff is extremely hard. So basically every time you like load in a Theano model, which will be like for a very small neural network, right? Let's say you have 2,000 images, like a convolutional network with 11 layers, it's gonna be like a gigabyte, right? Overall just data. If you like zip that up with like H5 or something like this, still 200 megabytes. So if you wanna like wrap this into like microservices or something like this, loading this up and like initializing everything, and then it compiles all the symbolic code, as Theano does. It's kind of horrible. And you basically cannot, and another thing, you cannot do this on the phone, right? And like what TensorFlow is doing is, like the speech API of Google that's running on your phone, or a lot of other stuff is actually using TensorFlow just normally because it's just easily embeddable on a phone, like Androids specifically. It also works on iPhones, I think, as well. So you can actually take your model, which is actually really small. It's like 5 times smaller than normal Theano models, and then run it anywhere. And also the other thing is, this is much more like much better suited for distributed computing, the way it is, yeah, because the model training is just an execution graph, and you can just run all the all the functions in parallel on different machines. This was not part of TensorFlow when it released, still isn't really. There's like free pull requests or something on GitHub. And I think you guys did something with that as well, it seems, like multi-tenant clusters. So we're going to see that. So that's kind of cool, because right now it's really hard to train a neural network. Like what you can do is spin up an instance with a GPU, like an Amazon instance or a Google one, and just train it. But the hope is, okay, I hope this will be finished in in a week, right? If you do like actually any meaningful data set, right? Obviously, like we don't do like data sets which are like a petabyte of images or something like this, you know, for like Linet from Google or something like this. But still, like even for small ones, it takes huge amounts of time. So actually trying stuff out, churn and stuff like this, takes huge amount of time with other frameworks. With TensorFlow, it's a bit faster. It performs a bit worse actually than the other ones in practice on GPUs. On CPUs, it's actually quite a bit faster. And what I found out that in like not small, like, you know, we're just trying things, it's much faster than like all the other frameworks really. So yeah, in practice, that's kind of it. And also it's very easy to deploy as a microservice, right? Because the model is very small, and then the inference, which is like the cool thing, is that a Theano model, for example, I think everybody knows, like if like most people know Theano is, it's like a deep learning toolkit. Because it compiles all the code and everything to run the neural network, every time you ask, like you try to predict something and not train, it has to go through everything, all the layers. And TensorFlow doesn't, because you can just do selective subgraph executions, right? And then that's like 20 million times faster. So you can actually very easily build up a synchronous service and have hundreds of requests like per second. Like last week, we're like at a hackathon, basically, where we didn't win.
How did you do?
Well, it's his fault. Yeah, okay. We didn't use Google PubSub, so it's a problem. No, like we could do basically streaming images. It was like a simple thing, like stream some plates. The idea was to stream wind turbines and see if they're defective or not. There's like a hole or something like this. We could do a few hundred images like in 5 seconds and we didn't really have any resources, right? We had just one service just running TensorFlow. And it was really fast. Compared to Theano, we could do like 5 requests like a second or something like this, even less actually. And it was a very, very beefy machine with like 64 cores and 200 gigs of RAM and like a very nice GPU. Yeah, so, yeah.
Okay, well, great.
Yeah.
And can you give us any specific examples of the industries or any specific projects that you have used TensorFlow with? What is the feedback from different kind of clients?
I have none.
Well, to be honest, at clients, we have not directly. Actually, in production, we don't have TensorFlow yet in production anywhere. Even deep learning in production is quite hard to get, because sometimes, actually before, the thing is before, as I said, with Theano and everything, everything was just too fat, and the models were too large and took too much startup time. And also the thing was, nobody actually wanted, you know, like with Theano or the other ones, even though, or even like, I don't know, like something like Cafe from Facebook. It's like runs on Lua, the other thing like runs on pure Python and compiles some magical code in the background. Like nobody wanted to have this in production or then servers. They're like, nope, we don't want to have this. TensorFlow, it's a bit easier because you just compile a C++ program and it just runs in not a program, but the framework. And the model just becomes just C++ binary in the background. It kind of runs. So we're actually like, I think we're going to propose this to much more customers, but potential industries are like anything, to be honest. Actually, automotive is like a huge thing, because like we had use cases for like automotive is like for like predictive maintenance, for example. Right. There was like a huge actually a thing about using recurrent neural networks to model the, you know, like the car is sending telemetry, but you want to like model what it's going to be like in the future without actually waiting for it or like using insane amounts of computing power. Like right now we're playing out like a bit very passively, but with an idea of generating all the future states of the car using a recurrent neural network. I'll probably use TensorFlow for this because it actually works quite well. Like it's not as fast as Theano, but it actually works like much more even, in my opinion. The other ones are, like, as I said, like the case for detecting broken plates. It was not the idea before. It was actually a real case of a company in Germany somewhere which has big wind turbines, and I won't say which company because probably I'll get sued for NDA stuff. But the idea is that you have very large wind turbines, and then they're like have very small holes or something on them, and there's like they're spread across thousands of kilometers. The idea is that the drone flies through and just takes pictures, and then people somewhere see like a classified, like a pre-sorting basically, right? You see that, okay, this is probably broken with this amount of probability, etc., etc. And this is also a thing where I think there's some guys actually around here that are doing something like this for buildings, right? They're like scanning, they're like taking satellite imagery of buildings and just seeing if there's something's broken or not. Like the scaffolding is like kind of bad, or like, you know, like all the instances of warehouses just basically falling inside because of the snow or something. Detecting those kind of things should be actually very well, because you can embed it properly. Yeah. So anything to do with images or text, in my opinion, or any time series analysis, works quite. I think that's what Google uses it for as well. It's mostly images and text, to be honest. I think Google Translate works like that. All the search of getting, like this is a cat. Everybody wants to find pictures of cats. That's also how it works at Google. And I think they're transitioning to using all TensorFlow across the entire entire infrastructure, because before it was disbelief, you know, the MapReduce, horrible. No, it's it's kind of horrible. Like MapReduce is horrible. We should stop using it. But yeah, but everybody's transitioning to that in Google, and that's like a good thing, because basically they're gonna write it anyhow. If the open source community doesn't do anything, they're gonna push it forward themselves. So like it's kind of good bet for industry, in my opinion. Yeah.
Oh yeah, great. Thank you. Can you give like a piece of advice for anyone who is just starting to work with TensorFlow? How long does it take to get productive with TensorFlow?
Can you repeat the question? You didn't hear me.
Oh, sorry guys. Sorry, my question is, can you give a piece of advice for anyone who's just starting with TensorFlow, and how long does it take to get productive with it?
Like the thing about TensorFlow is, like I'm just saying from my experience, right? And I've used deep learning toolkits before. Like the thing was, TensorFlow is like quite low level. It's actually very low level, to be honest, because you have to define a lot of things surrounding the model. But there's actually a lot of libraries, which deep learning libraries like Keras or something like this, which are quite good. We just use TensorFlow as a backend, which is actually very nice, because they also implemented like saving models, stuff like this, which was not in TensorFlow till like a month ago. You could not save models, which was kind of horrible, but okay. But now it works quite well. So what I would do is actually like Google stuff like wrappers around TensorFlow. If you just want to, I just want to create a quickly neural network and see if it works or not. If you want to actually understand how it works, just go on the TensorFlow tutorials or something like this. They're actually quite good. Actually, not on the tutorials directly. The documentation is quite good, but not that good. You should, unlike Google, actually weird. But you should go to the examples on the GitHub, and there's actually, what I would try to do is for spin up a convolutional neural network quickly. You can do this. Another thing for TensorFlow, because on CPU it's much faster than Theano, this won't take a day to train on like any of the, like MNIST, you know, like the usual thing everybody uses, the detecting characters, handwritten characters. This won't take like 4 hours of your life. You just wait for the model to train. It's gonna take an hour of your life to wait for the model to train, so it's a bit actually nicer. But what I would suggest is actually trying some wrappers around TensorFlow first to see how it works, to get the feel of it. Because if you're very new to deep learning, if you're not, just like literally try architecting the thing yourself, because the cool thing about deep learning is it's not really proper machine learning, it's more like architecture, right? You just like select things. There's a lot of machine learning, obviously, huge amounts, because you have to select the like proper layers and like what functions to use in certain things to avoid bias or like overgeneralization. But it's a bit low level, right? So if you're very getting started, you have no idea about deep learning, I would suggest something around TensorFlow. There's like like, there's probably a lot of guys who do Python or something. There's like scikit-flow, which is basically scikit-learn, but runs TensorFlow in the background, which is quite nice. So you can just get the feel of it and then go deeper, probably. No, that's what I did, basically.
Okay, great. And what do you think are the biggest challenges that TensorFlow has at the moment? Like, what kind of contributions from the community would be mostly valuable?
Well, I think like there's 3 things. I think actually I don't know, like a few things. The main thing is that like for me or my company it's not a thing yet, but for example, if you want to do any kind of video, like if you want to actually do video, like any machine learning on videos, right? TensorFlow doesn't support 3D convolutions, which means you like have to have always a 2D vector always, and then it just applies the convolutions like at certain parts of the thing. So there's no time. So that you can, there's no like 3D, like, you know, like 3D, what is 3D? You just have the vector, but also at different time steps. It actually doesn't support this yet. Doesn't work. Actually, there's a pull request, but doesn't work properly, I think. I haven't tried it myself because I have no access to video data sets, but yeah. The other thing is the, what was it? Yeah, actually checkpointing the model properly, like saving the model. Again, as I said, some other libraries implement this very well, but on the level of TensorFlow, you like kind of only checkpoint at certain executions, so you might lose stuff if you like kill it or something like this. It's not very easy to persist yet, like directly from TensorFlow. From other like stuff, other like libraries around it have done this already, but core TensorFlow is still a bit shaky on that, in my opinion. And the biggest thing is actually distribution, because you know if you read the if you read the technical paper of TensorFlow or anything, they always talk about running on different machines, and it actually doesn't. That's the funny thing. It only runs on different devices, basically on one machine. Like TensorFlow doesn't know if it's like a machine or like if it's a cluster or just one laptop. It runs by devices, so one CPU core, one GPU, stuff like that. But it doesn't distribute, like it has no idea if there's like more like computers there. As I said, there's like a pull request that runs this on Spark, which is a bit of cheating. It just basically runs a like just a tensor part of TensorFlow graph inside in Spark job somewhere, which is not like really good because TensorFlow already has the primitives to do this. There's another guy who did a pull request to do this already, and maybe you guys did something. This new to me, I didn't see this. Maybe it's like, maybe it works, so that's solved. So I don't know, but we'll see. So I think it's those, mostly that. So like saving the model is quite hard, distributing is like a bit not as good, and the 3D convolutions. The other thing was, I've tried this, like recurrent neural networks are really slow at the moment compared to Tiana or the other ones. The reason why is because you know, like in the recurrent neural networks, you basically have to go through, like you basically have to go over a piece of, let's say you have a text, you want to model sequence to sequence. You have to go over like all the words in a loop at some point in time. What TensorFlow does is you have a normal Python loop and it just generates nodes for execution of this. And like the other ones support very low level C-like symbolic operations. I don't know, I don't actually understand very well how they work, to be honest, but it's according to people, and I've actually noticed this as well. Like if I just compare the same network, like in the same library, like the same network, just using one or the other, one is noticeable, like Tiana is noticeably faster, basically. So it's those 4 things, my opinion, at the moment. But you basically can find this info if you go like on the TensorFlow issues and just see like the most commented ones. The community is insanely active on this, so I think they'll probably be solved in like a few months, really, to be honest.
Great, thank you. Alex, can you comment for us how open sourcing of TensorFlow influenced, well, the development of this very project? Are there any plans of well, you said you're not going to share any roadmaps or plans, but probably this open sourcing issue, how do you think it influenced the community and the Google as well?
Sorry, I wish I Should I have been prepared for that question? I guess I should have. But I don't know. I think there will be a lot of news. We have a big event in San Francisco in March sometime. I would assume there could be some more news and announcement around it. And when we have the second meetup, we can go into more details probably.
Okay. Okay, good.
All right.
So we're going to stay tuned for the news and the events from Google. Okay, so you guys have any questions to our experts?
Very maybe simple questions. I developed for myself years ago on mobile applications on the Android platform with the OpenCV to recognize things. And my question is, what is the most important advantages of TensorFlow over OpenCV? Because
like
OpenCV takes a really long time to create a model. When I try to train, I have to collect a lot of pictures and cut them and yeah.
Like, this is actually very good because I used to do a lot of computer vision, so yay. So well, the thing with OpenCV is, right, it's like it's the question of like comparing like basically designed features and just a thing that just learns features on itself kinda magically. To be honest, it's literally no, it's not magic, I'm joking, there's theory behind this. But the thing with OpenCV is that, like, let's say if you're using a normal global feature descriptor, actually no, local, sorry, like surf or sift or something like this, right? It's basically detecting like edges or corners, all of them really. Is just doing this in a lighting invariant way. So like scaling the image up, like grayscale and doing a thing, and then detecting, running per pixel histograms or all of this stuff, calculating the average of all of this, and then saying and then basically going on the maximum on 5 different levels, like trying to get the maximum 5 different levels for each pixel around a certain radius, right? And this takes a huge amount of time, right? This like literally takes a lot of time. But the thing is, like, it's not the training, I think, that takes a huge amount of time. It's actually doing this, just getting the descriptors of the features or anything, or just corner detection. Takes a lot of time on big images, especially on very large images. There's like basically in what we used to do in computer vision, resize everything to like 100 or 100 and use that to have any hope of running on a mobile device. And then the classifier itself is extremely fast, right? Training the classifier, just take a naive bias classifier, takes 10 minutes to train. It works okay, to be honest.
Me when I run the command to create the models, it will take around 30 minutes.
Yeah, because it was like scanning the image, resizing it, doing all of these things, getting the descriptors, so like 120, like in surf, 128 bits of things, and then trying the classifier. But if you just take the classifier, if you run all the pre-processing yourself, it literally takes like a few minutes. Compared to TensorFlow, where training will take 20 minutes for the same problem, like 520, or like, Tiano will take 10 times more. But then the actual prediction is like almost linear time, really.
Oh, yes.
Because it just like applies a function to every pixel and just that's it. And you just go through once through the thing and you're done. You don't have to detect anything or calculate properly anything. It's like just applying a few functions. And you can do this in parallel as well very well.
Okay, because my applications can now run on the mobile phone on Android platform, and it can recognize the things also in real time.
Yeah.
When, for example, when the car is driving through the street, the application can recognize those really well. But maybe I will take a look in the TensorFlow to
it just is the question of deep learning versus the classical computer vision world, basically. To be honest, some problems, there's no point running a neural network. Like, you know, we had this discussion of we're driving from Austria back to Munich, and when they're in a Mercedes rental car, right? And they were like off the road, the GPS wasn't working, but it still knew like that the traffic speed limit was changed because it detected, you know, the thing on the side of the road. For this, you would never use a neural network because it's a damn circle. it's like you literally say, okay, what's the biggest circle in the image? And you get it, and then it's very easy to understand, like, because you have like, they're all printed in the same font, all of them. So it's very easy to immediately understand if it's like a 60 or a 50 or a 80 or 255 million. No, it doesn't fit, never mind. Basically. But for more more difficult problems, like detecting cats, or like if there's a problem in an image, which is really hard for a human as well, deep learning is quite good because it actually generalizes very well to like really shitty data. Like that's my takeaway. There's probably guys here that like know this better than me as well, like, and the proper, like, I have not forgotten the math behind it as well. Yeah, but mostly that's like how, like, that's on a practical level, really that's it. Like some of the problems, like if you like face detection does very well with neural networks, it's actually quite a complex task. But if you're detecting rectangle, OpenCV is insanely fast. But anytime you have to do like a local lighting invariant, shadow invariant, scale invariant thing, it's insane. Like that's why it's written in C and very low level optimizations to make it fast. And that's really tricky. Like everybody who's tried to install OpenCV 5 years ago will tell you that they want to die, basically, because it's really hard to get it to work. But now it's much nicer. And TensorFlow comparison, just pip install it, you're done. Yeah.
Maybe another question. Is it possible with TensorFlow to create a model, I mean, dynamically without to have, any knowledge before? For example, we take pictures of of the crowd here, the people here attending the meeting today. And it is possible that we use TensorFlow library to automatically create models of, for example, to recognize the heads of the people here, or we have to cut the photos.
Sure. Obviously, I think there's like actually a really cool paper about this, which does like, it's actually from DeepMind from Google. I think it's like they basically have a recurrent, no, actually not. Yeah, they have a convolutional / recurrent neural network that models intention. It like slides over the image all the time, randomly, kind of not randomly. It actually kind of guided optimization search, slides over the window, and that's how it detects like faces everywhere. Actually, maybe if I found the link, I'll like, if we talk later, I'll maybe like send that to you. It kind of like basically it's, again, you have to slide over the picture. That's like, or like globally just detecting everything won't really work in my opinion. But maybe somebody's worked on this, but I don't know. Yeah.
Okay, any more questions?
Maybe one question, you mentioned language, natural language processing also as a great area. Could you tell us a couple of applications where deep learning is better than naive Bayes or any other?
Yeah. Well, to be honest, like as far as I know, the state of the art, like actually the best models for sentiment analysis or, like parsing, so tagging, adverb, verb, etc., are neural networks actually. Like this was actually pioneered by a guy. Oh, what was this guy's name? No, he wasn't a Google guy, a French guy. I don't remember him. No, it's not Lechun, it's the other guy. Okay, never mind. But basically, like neural networks have the state of the art of sentiment analysis, parsing a sentence, and also machine translation. They're like the best ones. Like none of the other models are actually as good. There's like huge papers about this, why this is the case, but in my but to be honest, I won't speculate because I cannot properly argue the point, to be honest. But what I've tried is, it's very nice for any type of sequence modeling, right? Because it's very hard to model sequences in any kind of classical machine learning model because you don't have the concept of loops or memory or any state management. Like if you have let's say you want to do basically, like example, you want to learn the entirety of like a representation of every word in a corpus of documents, right? Classically, what you would do is you would use bag of words. That's like the only way to do it, right? You just see like, okay, this word is with this, like this much, and you just basically assume this all corpus was generated from a generative process and just try to fit that process. And in contrast with recurrent neural networks, for example, you can say that this word comes after this word and this word comes after this word, and then the model generalizes to that and it learns that these words are usually together or after each other, right? Because you're just literally feeding the network one word at a time and asking it to predict the next word, for example. This is like, if you Google this, there's huge examples of this, of just I don't know, like feeding Nietzsche's work to a recurrent neural network and looping the network on itself, so the input is the output, just giving it one word and then it starts writing Nietzsche, basically. This is impossible with any other type of model, to be honest. I've never been able to, like, I don't know if it's possible, right? With any kind of classical classification or even prediction or regression model, right? Like, how do you do it? I actually don't know. Like, and recurrent neural networks kind of can do this because there's the whole concept of looping everywhere, right? Because it's just a graph of executions and you can just loop back all the time. But this is in very layman's terms, right? Obviously, there's like, I don't think we have time to discuss very deeply. But that's basically it, really, in my opinion.
Yeah, okay, thank you. Anyone else? This could probably be the last question from the audience so that we could be up on time for the talks, okay?
This is a question to Alex. I'm sorry. No. I mean, somehow TensorFlow seems to fit in the externalization of internal tools that you mentioned at the beginning. And my question is, why does this come now? And what are the advantages, or what is the motivation of Google to use or to externalize these valuable internal tools and open source them? Could you give? Yeah.
Well, we're not open sourcing everything. We're actually asking for money for some of these services, right? So if you use PubSub, Dataflow, etc., the idea is, I mean, Urs Hölzl, that you might have heard of, who runs all of our infrastructure, right? He said the whole cloud platform topic into that we got in really late could be actually bigger than our ads business, and he's pretty serious about this as well. So our ads business is about 50 billion a year, and we see a lot of potential in this market. You know, not everybody is running on Amazon yet. I know it's a very hard discussions in these local areas here, especially in Germany, talking to customers about cloud potentially, but more and more customers, even in the old guard and insurances, etc., are seeing that they cannot do the things they need to do on the scale that they need to do. They all know they're sitting on data, a lot of data, and Google worked like the Amazon services, like up to 10 years ago, but started more internally going toward managed services, taking things like Borg, right? So where a developer doesn't log into machines anymore, he just writes the code and say, go run in this many replications. That's a good example of automating as much as you can around the process. And this is very compelling to not just the digital natives, but also some of the larger companies that want to behave like digital natives, and you can just do a lot of stuff in very little time because you don't have the overhead of touching infrastructure at all, right? Things like BigQuery, uploading your data, doing queries, SQL queries over a petabyte of data and getting answers in a couple of seconds is pretty compelling and also a pretty good starting point for us when we talk to customers. But then how do you actually ETL unstructured data and these kind of things? We only now, like last couple of months, GA'd some of the last products in this area, and there'll be more coming, but that's kind of our motivation. We actually want to make money with this.
Thank you. So, Alex, Artem, thank you very much for your answers. And I think that if we are going to get started with the talk, I'm going to introduce Ankit Bahuguna of Cliqz to you, and we're going to have an overview of TensorFlow and try to... Thank you so much. By the way, folks, if you have any ideas of the topics you want to be discussed at our next meetups, please take notes on these colorful stickers. You have pens and pencils somewhere beside you, and there are more here at front, so you can get your ideas on the stickers, so that we know what you would like to get us focused on and what kind of speakers you would like to see next time. So Ankit,
Okay.
please.
So thanks a lot, Stylight, for and Altros for inviting me. I'm Ankit Bahuguna. I work for Cliqz as a software engineer, and today I'll present you an overview about TensorFlow. A bit of information about me. I'm actually working at Cliqz as a search engineer, where we are building a web-scale search engine for the German community. The areas which I'm really interested in are like information retrieval, machine learning, deep learning, and natural language processing. I completed my master's in TU Munich last year, and I have a work experience at TUM, LMU, Teradata, and IIT Bombay. And I'm also representing Mozilla since the last 4 years. And you can actually write to me at CodeKey, which is my Twitter handle. So a bit more about Cliqz. We are based in Munich. It's largely owned by Hubert Burda Media. We have an international team, which is like 27 countries with 90 experts in it. And we are combining data, search, and browsers together to give a seamless integration of a new experience of internet itself. And we have Android and iOS apps, and the web browser is like based on Firefox. We have a Cliqz extension as well, which runs on Firefox with anti-tracking enabled, which is quite a huge thing in Germany. So go through Cliqz and tell us how we are working on. So the outline today. So first, I'll just start with what TensorFlow really is and what it brings to the table. What are the mechanics behind it? And what is this thing called TensorBoard, which allows you to visualize your learning. There are some demos that I have prepared, some benchmarks which have been contributed by the community about how this stacks with other deep learning toolkits, and some of the applications that we have. And at last, I can have Q&A. So TensorFlow is, as we all know, it's like an open source software library by Google. It runs on both the single machine and distributed implementation. That's what the paper says. And with multiple devices like CPU or GPU. The code is itself written in C++ with Python API wrappers around it. The latest stable release is like 0.71, which was released around 10 days back. And the license is Apache 2 open source. And the website is tensorflow.org. So what is the usage of TensorFlow? So one of the questions in the fireside chat was about NLP. Since I'm an NLP person, so I can probably answer it. So one of the key things that was in the news by Google was RankBrain, which is the information retrieval engine behind Google.com, which is supposed to be the third most important signal for them. So that runs sort of the TensorFlow backend, where they're using deep neural networks to solve or understand user queries. The other thing is the inception image classification model, which probably people know about. That's the 2014 model, which won the ImageNet competition. That is also running, all the computer vision research goes on in Google with TensorFlow. They have a blog post on Google Research about Smart Reply, which is like an LSTM-based model, which automatically generates replies to your emails, the emails that come, and it's also in your phone. So in the Android, you can actually see how it works. There are also some collaboration with Stanford for drug discovery, where they can actually like identify strands of drugs, and that also uses deep neural networks. Again, collaboration by Google and Stanford. And the last one is an on-device computer vision for OCR, which you probably might have used already, which is the Google Translate app, which you can actually just take a picture, and in the real time, you can just transcribe or translate what that picture or the text inside the picture. It does something called optical character recognition, or OCR, and that also uses TensorFlow. So how is it different from all? So as we know, we talk a lot about like what that it can run on several devices. What it actually means is like it can not only run on your Intel CPUs, but also on ARM architectures. And most of your mobile devices are ARM enabled. And the reason behind it is like they don't use BLAS at C++ level. They're using something called Eigen, which is compatible to ARM. So you can actually then deploy this particular model that you train on, say, there's a research team in your office which is researching on some models, and then you want to just put that same model in the production. It's really simple because you don't have to give it to an engineer to optimize, to write a production level code, which is actually the case with machine learning, why people are not able to bring a production ready model so that people use it. The other thing that TensorFlow actually has is multi-GPU training, which if you have several GPUs, if you have used AWS infrastructure, the G2 machines, which actually allow you to have 4 GPU cards at the same time, you can actually utilize all those 4 at the same time and use it in the learning. But Microsoft, which has this thing called CNTK, they claim that they use something called 1-bit SGD, which is much faster, and they claim to be the fastest in this league. And yeah, they have some numbers to claim as well. It's very clean and modular architecture. If you look at the images, it's the CPUs, GPUs on the lower level are your devices. The yellow layer is the TensorFlow layer. It's the way the library is written. And at the top is the API wrappers that are around it. So if you want to add a new wrapper, say in Rust or Go, you can probably use that as well. So it becomes very easy for new developers or new languages to abstract that particular model out of it. So coming to the mechanics. So a TensorFlow computation is like a data flow computation, which can be represented as a directed graph, and a graph has nodes. The graph actually represents this computation, which actually provisions the nodes for maintaining and updating states. And it has some branching and looping support. The node actually represents some sort of an operation. An operation could be like an add, multiply, like a matrix multiply. The tensor is some sort of an arbitrary dimensional array, which is like n-dimensional array, which you can think about as between 2 nodes, there are edges, and on the edges there are weights. So tensors define that, and they are mutable, so you can change them. There are certain control dependencies, if you want to go from node 1 to node 2, what happens is you want to say, okay, there has to be some task which has to finish, or I want to just regulate this task. You can define that in the control dependencies. Then there is the operation, which is an abstract computation, again, add, matrix, multiply. The operation can have attributes. At the graph construction time, you have to instantiate that node, say instantiate all the variables. So this happens only once. And later I'll show in the demos how this works. The kernel is actually a particular implementation of that particular operation. So if I want to do matrix multiplication on CPU and on GPUs, probably the code could be different. The way it handles memory would be different. So you can actually write kernels for both of them. And as we see in the latest releases, that there are new operations that are being written, like fast Fourier transforms, etc. The whole TensorFlow system is sort of managed by something called a session. The session is what initializes your TensorFlow system to work. When you do session.extend, you can actually have one session, say you have a part of a graph computation, and you want to add some more stuff to it. You can do that session.extend to get some more information out of your already running system. The second thing is session.run. So when you create a session you want it to run, that is, say, training a model or evaluating a model or testing on your set, that you can then use using session.run. The variable is called a special operation. All this data comes from the white paper itself. So these variables are those which can actually, you can actually change, and this actually helps you to do this iterations of several training steps. So when you want a model to run 100 times, you want that state to change and some state to actually remain. This thing can be done using variables. And they have special operations within that operation that is called assign, like say your counter equals to something, and counter addition or increments. So that thing is stored in variables. The way it is implemented in the backend, it's they have a single this master and worker process architecture, where say if you are running it on a single machine, it's the image on the left. You have a client which actually accesses a master, and that has access to all the worker nodes. The worker itself has these several devices that are mapped to it. Now, devices are like CPUs and GPUs, but there is a registration mechanism, which they claim in the paper, that you can actually say if you want to have a new device, say a new chip which just runs a particular computation very fast, you can actually register that, and even that also takes place. So that's pretty cool. The other thing is the distributed implementation, which was the reason the paper was so highlighted about. which right now is not there in production, or in the master branch, is you can actually like have the same worker processes across several different systems in a cluster. So that will actually allow you to do some sort of a data like you can actually divide the data set, and you can actually like train these models on several CPUs, just like what MapReduce does. And you can utilize the cluster itself for training. And this is pretty useful if you are like dealing with a lot of data, say terabytes of data, and you really want to learn with several iterations and like several models altogether. So the devices itself are like named like this, like it's called job, localhost, device CPU, or some worker with a particular task and the GPU. That's how they define it in the code. The tensors are again a typed multi-dimensional array. They are typed, so they support like integers, signed and unsigned, IEEE floats, double, so all these complex types and string types. So you can actually like store these many sort of data items in it. And the beauty about this is that since the whole kernels are actually provided by Google, at least for the default algorithms, you can actually not think about what happens to the GPU memory, which is very scarce, or what happens to CPU memory. They are like handled all together, so it's pretty easy to start with. So this is like one piece of small TensorFlow code, again from the paper. So on the left side, we see the code. On the right side, we have something called the computation graph, which the code generates inherently. We start with like an import with TensorFlow as TF, and then we start variables. Initialization of B stands for bias, and W stands for weight. And X is like a single placeholder, which is your input. You can create a placeholder which says, okay, this needs to be fed consistently. Your tf.0 is 100, means I want an array of 100 dimensions with zeros in it. The second tf.random uniform. These functions are all defined in TensorFlow. Again, a 784 by 100 with like a uniform distribution between -1 and 1. Then we also have these things called rectified linear units, which are quite famous in ConNets sort of area, where you can actually have this nn.relu, that's a function, and you can define this wx plus b computation, which is your sort of what you use in this linear regression. And you can have your cost function, which is the loss function, based on some function of this particular ReLU unit. So it's same as any neural network. You have some inputs, you have some computation, you have some outputs, but you want to minimize the loss. And to do that, what you have to do is like, you need to define this loss function. And to run this several iterations into it, you define something called a step, which runs it, say, like this line for step in X-range, that runs it 10 times. With an input, again, you feed that input, whatever input that you have. So you have images or text as some n-dimensional arrays. Like here you have 100 dimensions. And then you do a run. So when you do an s.run, the entire thing gets initialized. And when you like write the code, you have to like initialize it. And you can provide this input vector. And C is your cost function. So based on your C, either you maximize or minimize that. It will run it n times. And then the last line will just print it. What computer, like the system itself, understands it is like a graph formulation of the thing. On the left side, we have W and X as the input to a math multiplication, that is WX. And then you do an addition to add the bias. And then an ReLU layer is there to get the output on the cost function. So this is how the system actually understands this code, this piece of code. We'll see in the example how it actually works. There is something called TensorBoard, where we actually can visualize learning. Often what we see is like when we are running a neural network and it runs over, say, several days, you want to find out whether your biases are is it converging or diverging, or is it really what you are looking at. And this is particularly good because, say, if you are really training on pretty high data sets, especially in size, then you probably want to know whether you are actually investing in the right computation power or not. So they have this thing called TensorBoard, which could say you can actually plot your losses, your biases, your weights. I have a demo about it, which you can use. And there are these NN biases. These are some these pictures, again, biases, plotting against time, some sort of time series data, what happens like in biasing or gradients or weights, how they change over time. So that you can actually say. And in the first figure, you can see the accuracy or whatever. This is the cross entropy, actually. That it decreases over time, which actually tells, like, given a neural network, whatever your outputs are, how well are they performing against the existing test set or the set that you already have. They have something called graph visualization. Again, as I said, there are these nodes that you can actually see that people can just zoom in or zoom out to. So given, say you have a 2-layer convolutional neural network and you want to find out what actually you have coded or what kind of layers architecture that you have, especially if your model is pretty complex, you can actually just look at it. You can't really tune anything, but you can just look at how your architecture is. You can save it. You can generate a lot of other information which can be useful for like good visualization of how it is performing. It also runs on like a serialized set of data. So as soon as your computation is running it, you can actually create a graph which runs like in real time, which is pretty good. This is one example of a CNN which uses like 2 or 3 layers, and it uses 2 convolutional neural layers, con1 and con2 at each level, and then it actually like feeds into a softmax linear layer and then a softmax layer at the top, and at the top we have a moving average. So just by looking into the graph itself, you can see how the convolutional neural network is actually like moving, and it's quite insightful in the sense. So let's have a simple demo of linear regression in TensorFlow. So yeah. So as I said, we had like, is it visible? Okay. So we have some input data, x and y, which is like an output function that I have. And let's say for the sake of simplicity, I have this form. Y equals to x into 0.1 plus 0.3. So w is 0.1 and x is 0.3. So what I actually want my neural network is to find out what are these values, w and x, given some random values of x. And I just feed the same thing. So I have a w, which is the weight vector, which is again a random uniform vector, which is between -1 and 1. A bias vector of like zeros. And then this is my input function. That is wx plus b. So I'm trying to do a linear regression. So I want to minimize the loss. The loss is the squared error loss, if you know about it. And the optimizer that I use is like the classical gradient descent optimizer. So for training, when I want to train it, so right now it's only initializing. We just initialize it. So we have an optimizer object and we do a minimize. We want to minimize the squared errors at each step that we have. There is this thing called init, where we try to initialize all these variables. These initializer variables actually initialize our w and b, which are like starting our variables that we had. And then we start a TensorFlow session. We start with a run function, as I said, with init in it. So all the initialization happens now. So until this thing, we just define it, and at this point, we actually initialize it. Then we try to do an iteration way of learning of how to get to it. So we say, okay, let's iterate to 200. And I want to train this. So I want to do this training function, which is minimizing the loss of the squared errors using this gradient descent. And at every 20 steps, I actually want to print it. So if we see it, which is like, so there you go. So it's pretty quick. Okay. So if you see this, we started with like some random values of w and x. Remember what we had in here? We had w as 0.1 and x as b as 0.3, and that is what we want in the end. So we start with some random value of w, that is 1.18, and some again random value in the distribution of the bias, 0.347. And then there are these several iterations after every 20 steps. It actually prints what happens. So it tries to minimize the overall squared loss. And if you see around 20th, it tries to converge it. So we have like w equals to 0.1. It's right able to come up with this. And x, the bias itself, is like quite close to 3, 0.299. So that's how it actually works. So this is like a very simple example to just see how linear regression works. The next example that we have is word2vec. How many people know about word2vec? Or know about what word embeddings are? Okay, so in general, word embeddings are they're pretty nice concept which was introduced first. It was introduced before, but like the first major release that was word2vec was by Mykolov. There was another release, it's called Polyglot as well, which was like an earlier paper. But anyway, Mykolov's release, which was while he was working at Google, was given a word, just give me an n-dimensional vector of that word. What that vector particularly signifies, say if there is a word, say box, and there's like a floats with like 100 floats array, which like a one-dimensional vector, or like a 100-dimensional vector, you can actually say that that box is dependent on like what is the context of that particular word. So the neural network actually learns a language model where we actually can see, okay, given this context, say the box is on the mat. So given this context, what should be the vector of the word? There's a complex mathematical way to do it. Probably I'll try to explain that in the code itself, but here it is. So again, I have done this part, that's the downloading part. So we have to download a data set. So it's like an unsupervised language modeling scheme. So given all the words in the corpus, or all the words that we have, what we want to know is what are the vector representations of those words in that corpus. So first we download a data set, which is like the same data set that the paper used in word2vec by Matt Mahoney. Again, we have some called reading the data, building the data set itself, and we generate a batch. So the batch is something like, he introduces two different particular models, skipgram and continuous bag of words. So skipgram is something, say, you have a sentence, the cat sits on the mat. So sits on the mat, if you just say one particular phrase, then given the mat, give me the context word, or what is the word before it, or what is the word after it. And you just do a window over the entire sentence, and you just try to learn information from it. So given that, what we need is like, if the next word in a given phrase is X, what is the preceding word, or what is the probability of this? And if there is a particular nice sentence, which is a correct sentence, the probability is 1. If we just have like a noisy sentence, like a word from somewhere, two words from somewhere, which will never correspond to one another, the probability will be 0. So that's what the main learning is all about. So again, given we have a batch size, an embedding size. Embedding size is actually the n-dimensional vector. And we have like a skip window, which is like how many characters or words to skip. This is done on words, by the way. And then there is what is a valid window, what are valid examples. And then again, you started like a graph initialization, which is like the default graph that you have. TensorFlow actually allows you to have more than one graph. Most of the computations that I have done is like which only use like one graph. Again, there are these training inputs, these placeholders variables, training labels, the valid data set. Again, you try to run it on a device. There are certain functions for this particular example which were not coded for GPUs at that moment, even now. So it uses this device CPU. So this particular kernel runs on the CPU. This line means this. And then you have a TensorFlow variable. So your embedding is like for each word that you have, whatever the vectors that you have, you just try to not store them separately, but store them in like one singular array. And it's done because it's quite performance, it gives you a good performance optimization. And again, given the vocabulary side, number of words that you have, and the embedding sides, so given the number of words and what dimension of vectors you want, you can create an X by Y sort of a array. And again, you want to initialize them uniformly, and then you can just create a lookup. So given that word, just give me the vector. Then there's something called noise contrastive estimation. That's the weight that the actual, so they use something called truncated normal. And again, vocabulary size and embedding size is the same. So use the same embeddings as an input, but try to reduce this embedding size as the square root of the embedding size. And the biases is a simple 0 vector. So again, we define the same weight and biases. And the loss is a reduced mean, which we want to like reduce. And we want to particularly reduce this NCE loss, which takes in the input of weights, biases, embeddings, and training labels. And the samples that we have are also dependent on that. The optimizer, again, is gradient descent optimizer, with which we want to just minimize the loss on. So we can just define it in one line. Again, if you want to do, what do we really want to do is, like, since a word is defined by its vector, what we really want to do as, like, say, how does it really perform, is we want to find out which is the closest word. So if there is a word or an alphabet, like say A, what should be the closest alphabet to it? Like, it should be some alphabet or not a word. So these sort of things that we'll actually see. And we have something called normalized embeddings. Like, we just normalize these vectors, say between 0 and 1. Again, it's the same lookup. And then we have a similarity. So we can do a cosine similarity or something. Now comes the part where we actually train it. So we have number of steps as, say, 100,000. And then we have a TensorFlow session. We initialize that. Again, this with session, so it follows the same thing. So as soon as the computation finishes, the session gets closed. You can actually, like, just have the session.extend to extend a new session, so if you want more information. Again, for the number of steps, we iterate the loop. We generate a batch. So we take the data, read the input in a batch, and then feed. This feed dict is actually the dict which provides you the input and whatever the outputs are. And again, we provide the session run, which actually runs the whole computation. So far, we just initialized it. And at the end, we have this average dodge, which we want to just add upon. And each step, what we do is, like, we give the nearest neighbors of this word, and we want to see how it's performing. So at the end, we'll see a good visualization of these words. So let's start that. So here it's starting. By the way, the model runs, like, if you complete the model, it takes a long time. So I have run it once, but I still want to show you what happens. So this is what we want to see. So nearest to the word from, in the first iteration, we get something like the sleigh, modernist, rain. And what we actually want is, like, these things to converge to some meaningful words. By meaningful, we'll just know in a moment. So as at each step, it actually tries to reduce this loss. From initially, we had 286. Now at 6,000 iterations, we have like 33. So as soon as we reduce it, we'll see some improvement in the kind of vectors that are learned. So we'll just see it in a moment. Yeah, so there you can see it. So if you can see, just see this nearest to is. So we have, like, things like was, as, has. There are some words which are still not, like, really close to it, but it shows the same form of the word is itself. Or, like, if there was some event or there is some event. So it comes in the same context. So the system is actually just learning it inherently. So this is the word-to-vec algorithm itself. So I'll probably cancel this. So it, like, does a pretty good job at the end. So if you look at what the final embeddings that are learned, are these embeddings. So if you just look at, so what we have done is, like, we have reduced those 100-dimensional vectors onto some 2-dimensional plane and just plotted those vectors. So the way we do dimensionality reduction is using TSNE, which people know about probably. It's again using some sort of a PCA sort of thing, but it does pretty good. Like, it does this dimensionality reduction of higher dimensional vectors pretty easily. So just look at the top one. If you just see the letters, they actually come quite close to one another. If you see the word, this thing, president, in 2D plane, you can have this George, Press, William, which probably are presidents in America, and they come pretty like close to one another. The other example is here. Say if you want to see directions, if you just look at this part, you have like north, west, south, central, east, much closer to one another than others. So the way we can actually use it, so given the word vector that you have, what you can actually do is simply learn those embeddings, and you can actually get synonyms out of it, or like say antonyms out of it, which are pretty useful in like several contexts. Or just if you know them as initial weights of your, say, recurrent neural network or an LSTM, which is like more complicated deep learning for language. You can initialize your vectors or your, say, right now I did a uniform initialization. You can do like a much better initialization where you have some information about the data itself. And that's pretty insightful, and you get some good results out of it. So that was visualizing word embedding. So as we have mentioned, like it's not as fast as the other frameworks are. And there was a study which was made like by Soumit Chintala from Facebook AI Research. This is done on TensorFlow 0.6, which actually clearly suggests like for say AlexNet or OxfordNet, for that particular data set, when we are running convnets specifically, that particular algorithm, say the Nirvana runs or CUDNNs